Now we've got this question on the board for us to solve and apply the knowledge of what we learned already regarding the relationship between these three molecular velocities that we discussed in the previous video. Let us look at this question please together. It reads, the mean square velocity of a certain gas at 27 degrees centigrade is x centimeter per second. What is I, its mean square velocity at 927 degrees centigrade? I, the velocity of the greatest fraction of this gas at 927 degrees centigrade. I, the average velocity. Now, let us see how we approach this problem, okay? The first part of the question, we are to obtain the mean square velocity at 927 degrees centigrade. But you know that before then, we have these values given to us from the question. Alright? So, okay, before I move on into solving this problem, I want you to put this down, please. Put this down, it's very important. This direct relationship between the mean square velocity or any other type of molecular velocity and temperature. Now, if you take your mind back to all the formulas we established for these three types of molecular velocity, you'll agree with me that all the velocities are directly proportional to the square root of the gas absolute temperature. That is why you would have the molecular velocity equal to this RT, square root of this RT all over whatever you have in the denominator. Is that not so? Now that tells us, because the molecular velocity is numerator equal to, then you see the temperature, square root, and the temperature is also numerator, it simply tells us that both of them are directly proportional. It means that if temperature increases, you expect the molecular speed to also do what? Increase. And of course, the consequence on the energy of the gas is that its kinetic energy will also increase. So please, I hope you put this down. We are going to apply that in an alternative solution to this first part of the question. However, I will solve the first part fully to show you the working, alright? Now, let us see how it goes. We have case 1 there. Case 1. We're given temperature to be 27 degrees centigrade, which converts to 300 Kelvin if you add 273 to it. Then under that condition, the root mean square velocity is equal to x centimeter per second. That is case 1. Now, thinking about the root mean square velocity formula, it is given as square root of 3RT all over capital letter M. That is molecular weight. Now, our problem is the molecular weight of the gas. We don't know it. The R, though, we don't have problem with that. It's a constant whose value we can easily select depending on the unit of this what? Root mean square velocity. Is that okay? So let's keep the R aside. Our problem really is the molecular weight of the gas. We don't know. So this is what we are going to do. We will use case 1 to obtain the molecular weight of the gas. And then with that molecular weight of the gas obtained from here, of course you know that the molecular weight of any gas remains the same. Are you following, right? It remains the same for that gas. So once we get the molecular weight, we can now substitute it in case 2. Alright, so let me write now that case 2, what do we know about case 2? We know the temperature to be equal to 927 degrees centigrade. This converts to, if you add 273 to this, you're going to get 1200 Kelvin. Now we have to calculate the root mean square velocity at that temperature. In that case 2, we don't know, alright? So this is what I will now do, like I stated earlier, from case 1, recall, we know the formula for root mean square velocity. Is that not so? Root mean square velocity is equal to square root 3RT divided by molecular weight of that gas. I hope you're following. So from there, we know that the root mean square velocity in that case 1 is x. So it implies that x will now be equal to square root of 3RT divided by what? The molecular weight. Now the temperature, we know the value of the temperature, so I can substitute. In that case 1, the temperature is 300 Kelvin. Alright? Remember from case 1, I want to make what? Molecular weight subject of the formula. So to do that, what will I do? I'll take square of both sides first. Are you following? this will become squares. X squared equal to 3r times 300 divided by what? N. Then making n subject of the formula is going to be 3 times universal gas constant times 300 divided by x squared. So take note of this. This is the molecular weight of the gas. So now go to case 2 now. From case 2, again we are going to write that the root mean square velocity at the temperature 1200, which we don't know, will now be equal to, you know the formula is going to be 3 times R times the temperature, which is 1200, then divided by the molecular weight. And molecular weight will have the value already, so it implies that the root mean square velocity under that case at 1200 Kelvin will now be equal to, come over here, then square root 3 times this, you know, you're going to have 3R times 1200 all over the molecular weight. And the molecular weight we obtained it to be 3R times 300 divided by what? X squared. Mathematically, this 3R will cancel this 3R. To divide, it give us 1, it goes off. Now, this 300 divide itself will give us 1. 300 can divide 1200 to give us 4. And this will eventually be equal to square root of 4x squared. You know that mathematically this x squared will go up. Is that okay? And then the root mean square velocity at 1200 Kelvin will now be equal to 2x centimeter per second. Square root of 4 is 2. Square root of x squared will give us what? X. So this is the answer. This is the answer. But there is an alternative way we can actually approach this question by, and then we have alternatively, can just do a simple direct proportional relationship. Are you following? Alternatively, we can say that square root of 300. You know, I told you that temperature is proportional to what? The molecular velocities. But the temperature, there is square root of the temperature, is that also? So I can say that square root of 300 would give us x centimeter per second root mean square value, is that also? Therefore, square root of 1200 will give us, we do not know, will give us y. This y now is what we are looking for. This y now is what we are what? Looking for. Let me indicate it. Where y is the root mean square velocity value at 927 degrees centigrade or 1200 Kelvin. Or 1200 Kelvin. Now coming to this, you can do cross multiplication, you know. We can do cross multiplication. But without cross multiplication, why not take square of both sides, you know? To remove this square root, you get 300 equal to x squared, and then 1200 equal to y squared. Is that not so? Then making y squared subject to the formula, that's going to give us 1200 times x squared. 1200 times x squared divided by 300. Are you seeing that, right? Because at this point you're meant to cross multiply. Okay, with this 300 will divide this. It implies that y will now become square root. If 300 divides 1200, you get 4. 4 times x squared. And that again would give us 2. Square root of 4 is 2. Square root of x squared will give us x in the unit of centimeter per cm per watt per second. So this is the alternative solution to this problem using direct proportionality principle. The only thing is for you to remember that when using this, the temperature initially has to be squared. The temperature initially has to be a square root. Are you following, right? And then in the process, you take square of both sides, then solve out and get your result.